So in this section, we are going to review the slopes of lines. So if you remember from Algebra 1, the definition of a slope of a line is the ratio of the change along the y-axis to the change along the x-axis between any 2 points on the line. Essentially, this boils down to the formula rise over run, which is equal to y2 minus y1 over x2 minus x1. The y2 minus y1 is what we call the change along the y-axis, and the x2 minus x1 is the change along the x-axis. So we're going to take a look at a handful of examples using that slope formula. So in this case, we're given the graph of a line and we want to find the slope. Well, there's two ways of finding the slope. You can do the rise over the run, which is a more graphical view, or you can do the formula y2 minus y1 over x2 minus x1. Now, from a graphical point of view, if we look at the rise over the run, we see that starting at point J, we go up 1, 2, 3, 4, 5 units. And we go with the run of 1, 2, 3, 4 units. So we can say our slope is 5 over 4. Now, if you wanted to use the points of J and K, we would first find their ordered pairs, which here we have -1, -2 for J. And for K, we have the ordered pair 3, 3. And we would substitute it into this formula. So y2 minus y1 would get us -2 minus 3. So -2 minus 3 over x2 minus x1, which would be -1 minus 3. Which you can see that we would get -5 over -4, which gets us +5 over the 4. So hopefully what you're seeing here is, if you are given the graph, it's probably quicker to just do the rise over the run, but you can also still use the formula. So let's take a look at another example. Again, we are given the graph, so we know m is equal to the rise over the run. So looking at the 2 points, L and M, we first start with the rise. In this case, we see that we're going down. We're going down 1, 2, 3, 4, 5, 6 units. So we have 6 in our numerator. And we are running 1, 2, 3 units. So 6 over 3 is our slope, which reduces to 2. Now, be careful with this, because when you look at this line and you read it left to right, you see that it's going downwards. This tells us we have a negative slope. So the slope should actually be -2. If you want to go one step further, you can go back to your labeling of 6 and 3 and think to yourself, we're going down 6 units. So you could say this is -6 and change our fraction to -6 over 3. Okay? But again, you should always be able to match the sign of your slope with how your line looks. If your line's going downwards, it should be negative. If it's going upwards, it should be positive. So let's take a look at this next line. Okay, so again, M is rise over run. Okay, and this is an interesting case, because notice from N to P, there is no vertical rise. Well, I shouldn't say there's no vertical rise. We should say that the rise is 0. Okay, it's not moving up, it's not moving down. However, we do have a change in the x. We have a run of 1, 2, 3, 4, 5, 6, 7. So we have to remember that 0 divided by 7 is 0. Now real quick, I do want to look at this problem using the formula to see why we get 0 in the numerator. And again, we want to relate it to this concept of rise. So before, we said that there was a rise of 0, and that's why we put 0 in the numerator. But if we look at the ordered pairs, n has the coordinates 1, 2, 3, 4, -4, -3, and p has the coordinates 3, -3. We can see that when we come to the formula, the y2 and the y1 have the same value of -3. So when we add those together, or excuse me, when we subtract them, -3 minus -3, that is how we get our rise being 0. Again, there's no vertical movement. You can continue solving the rest. You would get 3 minus -4, which again results in 0 over 7. So in the last example, we had a horizontal line where there was no vertical change, but now we want to see what happens where there is a vertical line. So again, we start off with the concept of rise over run. Okay? So starting at R, we see now that we do have a vertical rise, and the vertical rise is 1, 2, 3, 4, 5. So we could put 5 in our numerator. However, now we see that there's no horizontal change. Okay, from R to Q, it's moving neither left nor right. So we say it has a horizontal change, or a run, of 0. Now here's our issue. 0 is now in the denominator, which we cannot divide. We know it's an undefined answer, so we say it's an undefined slope. Again, let's take a look at this one algebraically using the formula y2 minus y1 over x2 minus x1 and see why this is the case. So let's first find the coordinates of Q and R. So Q is the ordered pair 2, 1. R is the ordered pair 2, -4. Using this formula, we can say y2, -4, minus y1, 1. We get -4 minus 1. But now, again, it's kind of the converse of what we saw in the previous example. The x values have the same value of 2. So the x coordinates have the same value. And when we subtract 2 minus 2, that's how we get the 0 in the denominator. Okay, so whether you're looking at it from a graph standpoint or a formula, you see that when you have 0 in the denominator, you get a vertical line, which ultimately has an undefined slope. So let's practice some more using the slope formula, except now we're not going to have a graph. So now we want to find the slope of the line containing the points 6, -2, and -3, -5. Now again, from algebra, you can label these points x1, y1, and x2, y2 if you choose. That's a common practice. This helps us with our formula. So remember, the slope is equal to y2 minus y1 over x2 minus x1. So this gets us -5 minus -2 divided by -3 minus 6. So now we just need to simplify, and be careful with your negatives. So here we have -5 minus -2. This essentially turns to +2. So we have -3 in the numerator. -3 minus 6 in the denominator gets us -9. Simplifying this, we get a slope of 1/3. Let's try another example using the formula. Now, a common question that usually comes up with using the slope formula is which point is x1, y1, and at which point is x2, y2? And the answer is it does not matter. What matters is that if I call this point or this coordinate x2, I must call this coordinate that goes with it y2. Okay, so what I'm saying is I can't say this is the point x2, y1. That's where you'll get issues. But as long as you're keeping your 1's and your 2's together, again, it doesn't matter which one you set as which. So going through the slope formula, we know is y2 minus y1. So we have -3 minus -2 over x2 minus x1, which is 8 minus -6. And so this gets us essentially 3 plus 2 in the numerator, which is -1 over 8 plus 6 in the denominator, which gets us 14. So your slope is -1 over 14. So we'll take a look at a couple more examples using the slope formula, and in this case we're going to have some special instances. So here we want to find the slope of the line containing 4, 2 and 4, -3. So again, if it helps, you can label your 2 points x1, y1, x2, y2. So now we want to find the slope, and we know we take y2 minus y1, which is -3 minus 2. Divide that by x2 minus x1. Hopefully you're noticing something here. The x2 and the x1 have the same value of 4. So when we subtract them, we know we're going to get 0 in the denominator. In the numerator, we are going to get -5, but that is really irrelevant because since we have 0 in the denominator, we know we're going to have an undefined slope. And again, if you want to think about it, this is going to get us a vertical line. And we'll talk more about that momentarily. So this is the final one we'll do using the slope formula. Again, if you prefer, you could label your points x2, y1, or x1, y1, x2, y2. And again, it doesn't matter which one you label which. So we start off with our y2 minus y1, which now, hopefully you're seeing is similar to the last one, except now the y values are the same. So y2 minus y1 is 3 minus 3. Well, the denominator, we have 4 minus -3. But now we get 0 over +7. When 0 is in the numerator, this can be done. And so in this case, the slope is 0. Now when you have the 0 slope, you can think of this being a horizontal line. So as we went through those examples using slope, we talked briefly about the types of slopes. Well, in this slide, we'll take a look at the 4 different types of slopes and be able to compare each characteristic. You always read a line reading left from right. So when the line goes upwards, we say it's positive slope. When the line is going down, it's a negative slope. Now there's 2 special cases are the horizontal lines. Okay, so horizontal lines have a slope of 0, and the vertical line that have undefined slopes. Always trust your slope formula, okay, in terms of your positive signs and negative signs, and when you have 0 in the numerator and 0 in the denominator. That will allow you to determine what type of slope you are working with. Now to finish up this section, we're going to start looking at at slope as the rate of change, which describes how a quantity y changes in relation to quantity x. So in this case, we have a pilot flying from Columbus, Ohio to Orlando, Florida. After half an hour, the plane reaches its cruising altitude and is 620 miles from Orlando. About a half hour later, the plane is 450 miles from Orlando. We want to predict how far the plane was from Orlando 1.2.5 hours after the takeoff. So we want to start by identifying some key points here. The first is we can write the half hour and the 620 miles as an ordered pair. Secondly, we can identify another key point, which we say is a half hour later. It is 450 miles. So a half hour later from 0.5 would be 1 full hour, and we said it's 450 miles. So let's plot those 2 points. So 0.5, 620 is right around here. The 1 and the 450 is right around here. And now we can use these 2 points in order to figure out how far the plane was from Orlando 1.25 hours after takeoff. Well, the first thing we want to do is find the slope between these 2 points. So we say that the slope is y2, so 450 minus y1, which is 620, over x2 minus x1, which simplifies to negative 340. And this is in miles per hour. Now, if we want to figure out how far the plane was from Orlando 1.25 hours after takeoff, we're actually going to introduce another ordered pair. This ordered pair is going to be 1.25, comma, y. Okay? Now we get the 1.25 because that is the x-coordinate of our new point. Okay, how far was it taken from 1.25 hours after takeoff? But we don't know what the y value is. That is what we're trying to solve for. How far was the plane? So here's how we're going to set this up. You can use either of these 2 points. I'm going to use the 450 because I don't want to deal with a decimal. But again, you could use 0.5 and 620 if you choose. We're going to use our slope formula, but we're going to use it a little bit differently. So we know slope is y2 minus y1 over x2 minus x1. Well, in this case, I'm going to use 450 as x1, y1, and I'm going to use this new point, 1.25, comma y, as y2. Now, again, what's different is we don't know what this y2 is. Additionally, we know what the m value is. The m is negative 340. So, I'm going to come over here. We say our slope, which is negative 340, is equal to y minus 450 over 1.25 minus 1. Again, using this formula, we say the slope, which is negative 340, equals y minus 450, y2 minus y1, over 1.25 minus 1, x2 minus x1. So now we're just going to use this to solve for y. So we have negative 340 equals y minus 450 over 0.25. We want to multiply both sides by 0.25 so that these cancel on the right. And so we have negative 85 equals y minus 450. And then the final step is to add 450 to both sides. And you get 365 is equal to y. Now, what we can do to check our answer is plot the ordered pair 1.25, 365 on the graph. So that's going to be somewhere around here. And what you can see is that falls in line with our previous 2 points, okay, creating a nice linear function. So this is the final example of this section, and it's very similar to the one we just did. So in this case, in 2006, 500 million songs were legally downloaded from the internet, and in 2004, 200 million songs were legally downloaded. We want to interpret the slope of the line and determine or predict how many songs will be downloaded in 2012. So first things first, we're going to say our years start at the year 2000. So in 2006, we're going to say the x-coordinate is 6. Furthermore, we're going to say 500 instead of 500 million. So our y values represent how many million songs. Okay, so 6, 500 is our first ordered pair. That tells us that in 2004, when there are 200 million songs, we can write that as the ordered pair 4, 200. So let's start by plotting those points. So 6, 500, which is right here. And then we have 4, 200, which is right here. So let's first find the slope. Again, use our slope formula. So we'll say y2 is 500, y1 is 200. Divide that by x2, which we'll say is 6, minus x1, which is 4. So this gets us a slope of 300 over 2, which can reduce to 150. Now this 150 represents the number of songs per year that are downloaded. So we could say 150 songs per year. Now we want to use this slope to determine how many songs are downloaded in 2012. Well, in 2012, again, we want to first write this as an ordered pair. We'll say it's 12, y, because again, we don't know how many songs there are. So we want to use one of the original ordered pairs. I'll use the 4, 200, because they're smaller numbers, but you could use either one. And we're going to use the slope formula. So again, using the slope formula, which is y2 minus y1 over x2 minus x1, we get 150 equals y minus 200 over 12 minus 4. Again, think about where these numbers come from. M is our slope, which was 150. Y is our y2. 200 is our y1. 12 is our x2. 4 is our x1. So now we just solve for y. So we have 150 equals y minus 200 over 8. Okay, I'm going to come up here for more space. We know to multiply both sides by 8, so times 8 times 8, so those cancel. We get 1200 equals y minus 200, which results in 1,400 million songs being downloaded in 2012. Again, this is the ordered pair. What year was this? 2012 or 12. This is the ordered pair 12, 1400, which we could always check by graphing. So coming to our graph, 12, 1400, we see that it falls right in line with our other 2 points